Hello everyone, Aaron here. Welcome back to Leetcode. Today we are trying to decide whether a graph is bipartite or not. So the problem is specified is that there is an undirected graph with n nodes, where each node is numbered between 0 and n minus 1. You are given a 2D array graph, where graph U is an array of nodes that node U is adjacent to. More formally, for each v in graph U, there is an undirected edge between node U and node V. The graph has the following properties. There are no self-edges. Graph U does not contain U. There are no parallel edges. Graph U does not contain duplicate values. If V is graph U, then U is in graph V. The graph is undirected. The graph may not be connected, meaning there may be two nodes U and V such that there is no path between them. The graph is bipartite if the nodes can be partitioned into two independent sets, A and B, such that every edge in the graph connects to a node in set A and a node in set B. Return true if and only if it is bipartite. So here, for example, this one cannot be bipartite because no matter what we do, we can't separate these two cleanly into two groups, whereas this one here we can say those two are in two groups and these two are in one group and these two are in a separate group. Now what they haven't said here, but is probably very important for this problem, is that for a graph to be bipartite, it has to be what's called two-colorable. Now graph coloring is all about, if we were to assign this node a color, say blue, none of its neighbors can be blue. So this could be red and this could be green and this could be yellow, for example. So we would need 4 different color. In fact, no, we could do better than that. This could be blue, this could be red, this could be red, and this could be yellow. We can do this one with 3 colors. But for a graph to be bipartite, we have to be able to do it with 2. And the algorithm here is quite simple. Go here, assign all of its neighbors. So give this one, say, red. All of its neighbors get colored blue. Go to them. All of their neighbors must then get colored red. If their neighbor is already assigned a different color, fail. So that's a fairly simple algorithm, but I think it's worth having a go at coding that up. So in here, what we want to do, we've got our graph, which is a number array, so that's an adjacency list effectively here. 0 is next to 1, 2, and 3. 1 is next to 0 and 2, so on and so forth. Well, effectively what we want to do is maintain 2 sets. Red is a new set. Let blue equals a new set. And then what we want to do is effectively create a queue. While there are things in the queue to look at, in fact, no. Jeez, I struggled to type that. And what we're going to do is we're going to start the queue at let's go with how do we want to do this? Yeah, let's do it with 0 in it to begin with. what I'm going to do is I'm also going to create a set of unseen things. And we're going to start at 1, I is less than graph dot length I plus unseen dot, I can never remember how these work, add, I guess, I. So while the queue length does not equal 0, in fact it's more than that, while unseen dot size, I want to say, does not equal 0, while there are things that we haven't seen. Actually, no, this is probably a better way to do it rather than having a queue. No, we're going to need the queue. Let next equals unseen get one unseen. We'll quickly write the get one function. So what we want to do is sum equals let item of set. I haven't used this syntax in JavaScript in ages, so I'm struggling a bit here. Sum equals item break return sum. Q dot push next while q does not q dot length does not equal 0. What we want to do is we want to let, it doesn't really matter how we do this, so let's do let I equals q dot pop net. Then we want to go to for let j equal let j of graph I. Is that how that works? No, j equals 0. Node, yeah, hang on. J is less than graph node dot length j plus plus q what we'll do is we'll do red dot add next, and then what we want to do here, let add to equals if red dot has node, oops, don't want an actual if here. We want to add to blue, else we want to add to red. If add to not in, let's go inside, outside, in fact. The idea here is if out outside dot has graph node neighbor equal graph node j. If outside dot has neighbor, return false. We have failed in our coloring. Else inside dot add neighbor q dot push neighbor. Return true. And then every time we take something off the queue, we want to do unseen dot delete node. Unseen. That got a little messy in the middle there. I think I need to pause for a second and check what I'm actually doing. So we have three sets, red, blue, and unseen. A node is always part of one of these three things. Initially, they're all in unseen. We have Q, which is initially empty. We grab something from the unseen set. Whatever it is. Hopefully 0, maybe, to begin with. We're going to add that to the queue, add it to next. And actually, we're going to want to remove it from there. Unseen.delete neighbor. Actually, if not unseen.has, in fact, no, if unseen.has neighbor, continue, there's no point looking at this neighbor again. And in fact, we can do that same logic up here. No, sorry, if it's not unseen. No, we want to do that. Doesn't matter when we see it. So let me try that again. So so we haven't seen any of them. 0, 1, 2, 3 are all in the unseen. We get one of the unseen elements. Let's say it's 0. We push that onto the queue, we add it to the reds in this case, and then we mark it as seen. Q.length does not equal 0, so the queue now has something on it. It's got a 0 on it. So we're going to take something off the queue. That's the 0. It's in red, so we're going to have inside and outside as blue and red. For all of its neighbors, which in this case is 1, 2, and 3, if, let's say 1, hang on, this check is a little confusing. Unseen.has 1, yes. We do that, no, continue. So what this is trying to check is it's Friday afternoon when I'm recording this, so brain isn't fully working. Unseen.has neighbor, so this is saying if we have seen it before, which is false, then continue, don't check it again. Otherwise, remove it from the unseen set. So 1 is now marked as seen. Outside.has neighbors. Does red have a 1 in it? No, it's only got the 0 in it, so that's okay. So we're in the else. So we're going to add it to the blue, and we're going to push it onto the queue. We're going to do the same thing with the 2. We're going to go do all the same checks. So we're going to push. We're going to set red. We're going to put 2 into the blue set, and we're going to put 3 into the blue set. All of those are outside of the unseen now. So we're going to take them off the queue one by one. So 3 in this case is going to come off the queue next. Red.has node. Well, that's false. So inside outside is red blue. So the neighbors of 3 are 0 and 2. So the 0. We have seen this neighbor before. Well, then we don't want to skip it. We actually want to double check that, don't we? Hang on, so if I get rid of that. If it's colored wrong, here's where I want to do that check. If we've not seen the neighbor before, then we want to add it to the queue. So we've checked the neighbor is good, and if the neighbor is good, then we want to actually work with it. Otherwise, don't bother. Now, so hang on, back to where we were. 0 is in red. These 3 things are in blue. 3 is where we are now. 3 has a neighbor of 0. Outside is set to blue. Does the neighbor hang on. Hang on. The node, this was red. These are all blue. Does 3 belong to red? No, it belongs to blue. So we're going to set inside to be red, outside to be blue. No, I think I've got this back to front here, don't I? Let's try swapping these to make it easier. So the node is inside one set and outside the other. If the inside, if the neighbor is inside the same set as the node, that's bad. Give up. Otherwise, if we haven't seen the neighbor before, then we want to do outside.add neighbor. The neighbor is added to the set that we're not part of. All right, let's try this again. So we're going to make 0 red and push it onto the queue. So then for each of its neighbors, we're going to add them to blue. Now we get back around 3 is a blue. We're looking at the 0. So red is in blue. So 3 is in blue. So inside is blue, outside is red. If 0 is in blue, that's bad, but that's okay. We've got that. Otherwise, if we haven't seen the neighbor before, well, we have seen the neighbor before, so stop. Then 2. Yeah. So we're looking at 3 and 2. 2 is, so blue is inside. 2 is inside blue. So that's bad. Stop. Okay, I got myself tied up in knots there, but I think that's correct. Let's give it a quick go, just so I can catch some typos before we get too far. There's always one. For example, that one. Cannot find name node. Did you mean node? Next. Let's try that again. That's better. Let's use all the example test cases. That's not good. What on earth? JavaScript heap out of memory. What? Hang on, let's see what's happening with the second example. So 0 goes in red. 3 and 1 go in blue. 3 is in blue. 0 is in red, so that's fine. 2 isn't in anything yet, so we're going to add it to red. 2 has neighbors of hang on, I never take anything out of unseen. There, I should be doing that. There we go. That was my problem. I wasn't actually taking anything out of unseen. Right. Probably might be a little slow, but let's have a look. Doesn't hurt to try. Fingers crossed. Hey, perfect. We're actually pretty fast too. Faster than 78%, so nearly top 20%, top 25% quite comfortably. And completely middle of the pack for memory usage. Again, don't know the distribution on these. I would expect it's all pretty tight unless you're doing something wildly wrong. Not gonna lie, after the last couple of days, this has been a refreshing change, one I can actually solve. But yeah, hopefully that was entertaining. Thank you very much for watching, and I will see you all tomorrow. Bye. Jesus, I struggled to type that.